Okay. So let's talk a little bit about the Mobius strip, and then you're going to see some other things that shapes that we can do, and we'll see the projective plane. So if I take a normal sheet of paper and I don't do the flip, no twisting, no half twist, and I just identify these two sides together without the flip and bring them together, what shape is that?
That's just a piece of paper with no twists.
Okay.
Cylinder.
So show that to me.
So that's you doing this.
Okay. All right. So this is just kind of the interesting notation that we see, and so you can imagine, somebody walking this way, and when they come around over here, they end up
The same way.
the same way. Okay.
Eraser.
Okay. How would you, with this kind of notation, make it's just easier to redraw the rectangle. How would you describe the Mobius strip to me?
So, if you've got up arrow over here, you could do like a down arrow over here.
Okay. So, right. So now when we have, I'm not going to try to draw the person because I'm going to have to draw it upside down. When you walk off this edge, you reappear over here
Upside down.
upside down. Okay, and we saw that in our Mobius strip. That's why I was showing you the arrows.
Mm-hmm.
When you complete one circumference, or what appears to be a circumference, you get back to where you started, but you're upside down. Okay, so you actually have to go around twice to get back together. So now I want to give you another challenge before we talk about the projective plane. I want you to show me what a torus would look like under this description.
So I think a torus would be like this. So you kind of, this is not going to work this way, but you kind of fold this into a loop,
Mm-hmm.
and then if this loop were longer, like if you had like a tube, you fold these edges around so that they meet. I can't do that with this sheet of paper.
Right, so that they meet.
Yeah.
Yep.
And then you would get a torus. So that's very good. So if you're walking around a torus, if you walk around the loop, we'll call it the outside of the donut, you don't ever flip upside down. And if you walk through the inside, if you think about the donut, you don't ever get upside down. This shows something interesting, though, that geometry on a donut, on a torus, on a true torus, is actually also flat. That's not true on the donut or bagel that you see.
Yep.
Okay. Because it's the true torus is actually in 4 dimensions, believe it or not. So now we saw something very interesting with the projective plane. I want you to draw for me the arrows and the alignments that we saw in our puzzle here.
So you flipped going this way, and you also flipped going up or down.
Yeah, you flip going this way and you actually flip going up and down. And so this is what is called the projective plane. Okay?
Mm-hmm.
Yep.
And so you can see that this is different than a Mobius strip.
Yep.
And you can also see that it's a little bit strange because we start out with our Mobius strip. We're identifying these pieces reversed.
Yeah.
And we're identifying the top and bottom reversed. Okay? But if you can see, when I make the Mobius strip without the identification of the top and bottom, it only has one edge.
So it somehow has to have two
Right,
edges.
so if I follow this edge around, there's only one edge. So this is a very difficult object to picture.
Yeah.
Very difficult object to picture. And there's actually a third, actually I've lost count of how many objects we've talked about. But there is actually a different object where you identify, with the Mobius strip you don't do anything with these top and bottom pieces. But there's another object that you identify the top and bottom going in the same direction. And this object, do you have any guess about this object? What this would be on?
Klein bottle?
Yeah, I think it's a Klein bottle.
You're right, this is a Klein bottle. And then I have one last challenge for you. What is the shape that looks like this? Or what shape do you think this describes? I have a rectangle, and instead of identifying just the edges together, I identify all points on the edge. All edge points. In other words, make all these edge points be the same point. What shape is that?
So all the points are mapped to each other?
Yeah, everything on the edge becomes the same point.
It'd be sort of like rounded out. Maybe a.
Just a point?
It'd
No,
sort of
because
be
there's stuff on the inside.
Maybe a cone, because like you have all of the edge points, you're going to be connected to one point at the top.
So this means that if you go off an edge, you reappear in the same spot.
Well, you could reappear anywhere.
Right, you could reappear anywhere. So all these points on the edge become mashed into a single point when you fold it up. So what shape do you think that is?
I'm kind of thinking of a cone, but I don't think that's it.
It might seem like it might be a cone. This is actually a sphere. So you can imagine like all these points are roughly the North Pole.
Yep.
And from the North Pole you can actually kind of leave in any direction. So that's some interesting topology. And yeah, some of the stuff that's going on with this puzzle. And it's interesting for our puzzle, it says it was inspired by the Mobius Strip. But then they explain further that the shape that this puzzle is actually
It's a projective
a
plane.
projective plane. It's really cool.
Yep.
All right, good work this morning, guys.